Okay, hi. I'm Sarah Spall. I'm a PhD student at Indiana University, and I'm going to talk about our paper, Forward Build Systems Formally, which is joint work with Neil Mitchell and then my advisor, Sam Tobin-Hochstadt. So, starting with the basic idea of what is a build system. So, a build system just describes how to build software in a reproducible manner, and it gives you benefits like incrementality and parallelism. So the most prevalent type of build system is a backwards build system, which is basically just make. And so you write your build script, you specify what you want to build, and you say what it depends on and how to build it. So using this information, the build system can provide you with incrementality, and it can provide you with parallelism. And what does it mean for a build system to be correct? Well, to paraphrase the paper Build Systems a la carte, which was a paper that did an analysis of backwards build systems, a build system is correct if re-executing the build script is always equivalent to executing the build script from scratch. So basically, assuming the build system actually ran the commands you asked it to, it did the work. Building incrementally will always be equivalent to doing a clean build, right? So that's our intuition idea of what it means for a build system to be correct. And so given the challenges of writing a correct build script, like if you write a make build, you have to get all the dependencies correct or your build might not work as you expect it to. An alternative is to just write a shell script where you just write the list of commands that you need to build your project. And the benefit of this is it's really easy. There's no targets, there's no dependencies, but the downside is you don't get incrementality, you don't get parallelism. Every time you run your script, every command is going to run. So an alternative to that, to a shell script, is this less prevalent type of build system called a forward build system. And it's simple like the script, but it has the goal of still giving you incrementality and parallelism. So when we consider the behavior that we'd like our build system to have, ideally we would like our build system to do no work if there's been no external changes. So you run your build and then you immediately rerun it. You want it to do absolutely nothing because nothing's changed. And so we call this property idempotence. And here's an example on the slide of an idempotent build script. And this is actually an example written in the forward build system Fabricate, which this is just Python code. So here is an example of a non-idempotent build script. And it's because this build script modifies its own input main.c. It reads from it in the first command, and then in the second command, we change it. So if you run this build script again, it's likely going to rerun the first command. And we refer to this behavior as a read before write hazard. And so additionally, if a build script writes to its own output more than once, which here in this example is the file main.o, the first command that wrote to that file is likely to execute again if you rerun the script because its output changed. And so we call this a write before write hazard. And so in summary, we define these two types of hazards, which if they're in your build script, they could lead to your build script not being idempotent. So it doesn't have this desired property that we want. And so finally, I come to our correctness definition for forward build systems, which says a forward build system is correct if, for every build, it either produces the same result as running the build as a script, or it reports an error. And by error, we mean one of the two hazards that we just described. So either running your forward build system is exactly like running that shell script, or it says that your build has a hazard. And this is equivalent to the correctness definition for a backwards build system, just with the addition of the error. Okay, so in the rest of this talk, I'm going to briefly talk about our model of forward build systems in Agda, and then talk about two forward build systems that we modeled, Fabricate and Rattle, and then tell you the correctness definitions that we proved for them. Okay, so our model is in Agda, and here's just some basics. We model commands as strings, which it's not really important what the representation is, just basically we need to like compare equality between them. And builds are just lists of commands. And then the file system is just a mapping from file names to file contents. And we model command behavior as a function from file system to the files that a command read and wrote. So for different file systems, the command will read and write to different files. And then to run a command, you just give a command its file system, and then you extend the file system with the files it wrote to. So some of the assumptions that our model makes, and some of these assumptions are just for simplification purposes, and some of them we make because Rattle, our main focus, makes these assumptions in its own build. So first we assume commands are deterministic, and we also assume they don't write to their own inputs. We also assume that tracing data is correct so that we know exactly what files a command read and wrote to. And we assume builds are static lists, that the commands in a build are run sequentially, and that builds don't contain duplicate commands. So probably the most important of these assumptions is that I said that builds run sequentially, but we want to model parallelism. And so in reality, the build system Rattle runs things in parallel, right? And when you run something in parallel, you have commands that are concurrently modifying your file system, right? And so if our model is running things sequentially, it's not concurrently modifying the file system, right? But we model parallelism by different orderings of commands. So two different orderings of commands represent different parallel executions. And we believe this is okay because if you have a real execution of a build and there's commands running in parallel and they're writing and reading from the same files at the same time, that would be a hazard. So you can represent all acceptable parallel orderings of commands as different orderings because they would not have hazards. If two commands don't write to the same file or read from the same file at the same time, there won't be a hazard, and you wouldn't care what order they modified the file system. Okay, so because we use what happens with a script as our basis of correct behavior, we model in Agda a script, and this function just runs each command in the build. That's all it does, is it calls run on every command, and that's how we model a script. So the first forward build system that we model is Fabricate. And a Fabricate build script is written in Python. This is an actual Fabricate build script. So the commands are traced when they're run, and then they're recorded in a memory with the files that they read. So when Fabricate decides if it wants to run a command, it looks in the memory and says, oh, have I run this before? And the reads haven't changed. Well, then I don't need to rerun the command. But Fabricate doesn't check if your build has hazards, like the hazards I just talked about. It doesn't check for those. So what happens when there are hazards, we don't know. And so our model of Fabricate is just an extension of the model of a script, but it has a memory. And the memory is just a mapping from commands to files. So if you've run the command before, there will be a mapping for it in the memory to the list of files that it read in this case. And so we just have a new running function that checks the memory before it runs a command, and it extends the memory after it runs a command. Otherwise, it just runs every command in the build. So the correctness definition we proved for our model of Fabricate says that Fabricate is correct if for all hazard-free builds, executing a build with Fabricate has the same effect as running it as a script. And this correctness definition specifies that the build contains no hazards because Fabricate does not check for hazards, so we don't know what the behavior of the build would be like if there's a hazard in the build. We can't guarantee that it will do the same thing as the script in all situations. Okay, so the second forward build system that we model is Rattle. And Rattle is a forward build system that's implemented in Haskell. A Rattle build script is a Haskell program that can use arbitrary Haskell libraries. And the commands that you want Rattle, the build system, to run are just passed explicitly to Rattle via this command function. So Rattle has no idea about any of the Haskell code in your build script. It can have all this Haskell code. It doesn't interpret it or anything. And so Rattle supports dynamic dependencies, meaning that future commands can depend on the results of previous commands. And Rattle also supports incrementality and parallelism, even though you don't have to specify any dependencies. And it does this by tracing the commands and recording the files that they read and wrote to. So how does Rattle provide parallelism? It does this thing called speculation, which means that it takes the list of commands you ran last time you ran your build script, and it speculatively executes them in parallel before you ask it to. So when you run a Rattle build, you say, please run the command gcc-c foo.c, and it'll run it for you. But if you're running a build speculatively and you'd run that command before, Rattle might run that command ahead of time before you asked it to. And so when you actually ask Rattle to run that command, it doesn't have to because it's already done it. And so this is how Rattle achieves parallelism. Okay, but because Rattle is doing the speculation, it's running commands possibly in the order you didn't ask it to, things can go wrong. And so we have another type of hazard called a speculative write before read hazard, which means that Rattle speculated a command that wrote to a file that a later command that wasn't speculated read from. Basically, this just says that we ran the commands in the wrong order. Rattle did something wrong, something's gone wrong. And so when Rattle runs a command, after Rattle runs every command, it checks for these hazards that I just talked about, all three of them, it looks for them. And if it finds a hazard that was caused, if a hazard occurred and Rattle ran the build with speculation, it attempts to rerun the build sequentially with no speculation, hoping that it'll succeed. Otherwise, it terminates because the build isn't idempotent. It doesn't meet the requirement of being idempotent. So our model of Rattle, just like Fabricate, extends the behavior of the script with a memory. But unlike Fabricate, Rattle checks for hazards. So we have this new run with error function, which asks the memory, should I run this command? Has it been run before? Does it need to be run? And then it runs it, and then it extends the memory. But it also does hazard checking, and it checks if there are these three types of hazards I talked about. And it either returns evidence of a hazard, or it returns a new file system. And so here in this function, you can see that we split on the result of run with error. If run with error returns a hazard, which is our first case, then Rattle just returns a hazard and quits. Says we found evidence of a hazard, or it just continues and executes the rest of the build. So I previously said that real Rattle, the real thing, tries to rerun your build sequentially if it fails, but in our model, we don't try to do that. We just terminate. Okay, so Our first correctness definition for Rattle is for sequential Rattle, which is just Rattle that doesn't try to do anything in parallel. And it says that sequential Rattle is correct if running a build with Rattle results in either a read before write or a write before write hazard, or a file system equivalent to the one produced by running B as a script. And this is just exactly the same as the correctness definition we said before for forward build systems. And we additionally have a correctness definition, which we did not prove, for speculative Rattle, that says speculative Rattle is correct if the script either contains a read before write or a write before write hazard, or executing the speculative build with Rattle is equivalent to executing the script build as a script. And this is equivalent to the previous correctness definition because we are just requiring that the two orderings of commands are equivalent. Executing them has the same behavior. But we can't prove this. It's not true for Rattle currently, because although it is extremely unlikely, it is possible that Rattle could reorder commands in a way that overwrite build inputs. So basically, in this example, Rattle decides to run command A before command B, and command A writes to command B's input. But we were really supposed to run them in the other order, and in the other order, command A doesn't write to that file. So if we were to try to do Rattle's attempt to just rerun the build sequentially, it would fail because we've destroyed an input, and now we're not going to get the same result as we meant to, right? So that's currently is not true for Rattle. And so we have a weakened correctness definition, which we did prove, which says that speculative Rattle is partially correct if either the script build contains a read before write or write before write hazard, or the speculative build contains a hazard, or executing the speculative build with Rattle is equivalent to executing the script build as a script. And this is just the previous definition, except we've added this extra clause that it's partially correct if speculation leads to a hazard. So, and well, in conclusion, we've stated a definition of correctness for forward build systems, and then stated improved correctness definitions for two specific forward build systems, as well as a partial correctness definition for the second build system. Yeah, thank you.
We've already a question here locally. Owen, if that's okay with you.
So I have two questions. Was the incorrectness you discovered in Rattle known before you started trying to prove correctness?
I would say if we thought about it, yes, it was known. It's not like a crazy problem,
did anyone, you or otherwise, know it explicitly out loud?
I don't think so. Maybe not.
Okay, cool.
So, yeah.
That's why we do proofs. And my other question is about these tracing build systems in general. I have a directed acyclic graph in my big build of VST, and I know which specific edges take a really long time. But make-j doesn't know which ones are going to take a really long time, even though it's seen them take a really long time like 100 times already. So do any of these build systems trace not only which files are read, but how long things took in order to schedule the parallelism better?
Oh, to schedule it better. I would say no. I would say it would be, doable to tell you how long each of the tasks took so that you could see that information. But I feel like Make could do that for you too if it wanted to. Yeah, so I don't think any of them currently do that.
I have a question online for you from Dan Fruman of the University of Groningen. Is the presence of hazards a syntactic condition, or is it defined semantically?
Sorry, can you repeat that? Did you say the
Um,
present of a hazard?
Yes, the presence of hazards a syntactic condition, or is it a something that is defined semantically?
I would say it's semantic because, well, I mean, if I read through your build script, I could possibly tell you that there's a hazard in it just by reading the commands, but they're they are dynamically discovered through
Okay.
execution.
I have one more question
there-
here.
Yes.
Hi there. Good talk. So one of the features that you're using here is you're using tracing in order to get the dynamic behavior about which files were read and written. I was wondering, I mean, it seems like if you had a static approximation to it, then you could avoid doing some speculations that might fail. So I was wondering if you thought about providing some static analysis of read-write dependencies as well as the dynamic analysis?
Yeah, actually, we have talked about that for a different reason, but yes, we have. I'm not sure how hard that would be. We've definitely discussed that.
Okay. I don't see any more questions online. Are there any more questions in Philly?
No.
Okay. Well, let's thank